Okay, hello everyone. You should be hearing me. Just give me a thumbs up again so I know that some of you are listening to the stream and it's actually coming through. Okay, excellent. I guess after a while some of you will catch on to that and just give me the thumbs up without even without even hearing me ask for it. So please don't do that. That might be confusing for me. Um, okay, so last time we talked about the one-dimensional kinematics problems, and so we're going to continue that today. More one-dimensional kinematics problems. In particular, we're going to apply this to the main example of one-dimensional kinematics, which is free fall problems. Essentially, take something and drop it on the ground. That's going to be free fall, a key type of problem where we can deal with one-dimensional kinematics. It's just moving along the vertical, and it has constant acceleration, which is something we'll look at. Before we get to that, though, let's first talk about a recap on these one-dimensional kinematics problems that we talked about last time. And let's start by looking at the formulas. So we're going to use constant acceleration and then free fall motion. This is my recap of or my summary of what we're going to do today in terms of the one-dimensional kinematics. But let's start with a couple of questions, just kind of concept questions, similar to the question that you might have thought about for the homework assignment today. So let's look at this graph here, which is velocity versus time. So you can see there's different points marked on the graph here, A, B, C through L. This is the velocity as a vector quantity in a one-dimensional problem, and the time on the x-axis here. So the question is, when is the acceleration 0 in this graph? And so there's 5 answers here. Use the numbers to vote here in the class. 1, 2, 3, 4, or 5. Is it at point A and L? Is it at point D and H, right here and right here? Points F and G, or between points F and G? Is it at point E? Or is both points, both answer 2 and answer 4 correct? So I'll give you a minute to think about that, and then let's all vote at the same time. So for those of you who are just joining, we're going to give it another 30 seconds here. So think about when the acceleration is 0. At which point here is the acceleration 0? Another 15 seconds. I see many of you are already putting the answers in the chat. But let's vote all at the same time in 5, 4, 3, 2, 1. Okay, let's see what answers we have. Okay, I see many question marks, which in this case is the correct answer. So both answers 2 and 4 are correct. The points where the acceleration, the times when the acceleration is 0, is when the velocity is not changing. So at point D here, we're at a maximum in the velocity. Instantaneous acceleration is 0. Instantaneous acceleration at point H is 0 because we're at a maximum in the velocity. At point E, we're in a minimum of the velocity. So again, instantaneously, the velocity is not changing. So points D, E, and H are the right answers. So both answers 2 and 4 are correct. Okay. So let's do this again, but let's make it a little bit more complicated. Next question. Same question, actually. When is acceleration 0? But now I'm giving you the position versus time graph. So when is the acceleration 0 in this, or which answer is correct. So I will say in advance that there are other times when the acceleration is 0, but only one of the answers here is indicating a time when the acceleration is equal to 0. So this requires a little bit more thinking. Let's again give it a minute. So think about when the acceleration is 0 here. So now you're given position versus time. So you'll first have to think, well, what does the velocity versus time look like? And then you'll have to think, what does the acceleration versus time look like? Okay, let's give it another 30 seconds here. Okay, 15 seconds. And let's vote in 5, 4, 3, 2, 1. Okay, let's vote. So I see lots of 2s. This is clearly an answer that everyone's loving. Lots of hearts. Excellent. So that's indeed correct. So let's see what happens here if we turn this from a position graph into a velocity graph. So here the position is going down as time increases. So that's going to be a negative velocity. And then here we get to a point where the velocity turns positive. Now here we're still at the point where the velocity is positive, then it turns negative again, it turns positive again, and every time when the velocity changes from being increasing to being decreasing, that's when there will be a change in the sign of the acceleration, and the acceleration will be instantaneously 0. So when is that? Not at the times when we have a minimum and a maximum, but it will be when the direction of the change in the slope is changing sign. So here we're at a positive second derivative until somewhere between point I and j, and then as soon as we reach point j, we're at a point where we have a negative second derivative. For those of you who are in math, what is it, 1500, this is things that you will likely learn a lot about in the next month, and so thinking about derivatives is going to be important, but you'll learn about it as you go along in Intro to Calculus. So indeed, answer 2 was correct. Okay, back to the formulas here. So these are for numerical problems. These are the formulas that we went over last time. So the different types of formulas are how to use average velocity, v with a bar over it, which is the initial velocity plus the final velocity divided by 2. So we can write the displacement in terms of that average velocity. We can get velocity from acceleration. So final velocity is initial velocity plus the acceleration times the time. We can get position from velocity and acceleration. And we can get velocity from initial velocity, distance, and acceleration. Those are the formulas that we are going to use for these kind of problems. And we derived them last time. So how would we go about solving problems in kinematics? Well, the first thing we'll want to do is identify what it is that we know, identify what it is that we're asked for, and then of course pick the right formula here. If we are given initial velocity, final velocity, and an acceleration, and we're asked for the time, this is likely going to be the equation or the expression that is going to give us the answer that we're looking for. If we're given the time, the initial position, the initial velocity, and the acceleration, then this will be the equation that we'll use to find the position. So yes, it might be plug and chug, but in some cases it will be not as straightforward as plugging in the right hand side to get the left hand side. For example, you might be given the distance between the initial point and the final point, and the initial velocity and the final velocity, and you might be asked to calculate the acceleration. So you might be asked to calculate a from that last equation here based on the values for v and x0. So let's do a couple of examples for this. Let's start with this example here. We have a dragster, so a constant accelerating car that starts at position x0 with an initial velocity v0, which is 0 because it starts from rest. And the dragster travels for 5.56 seconds at that initial acceleration. So, first question, what is the coordinate x at time t? So after 5.56 seconds, what is the coordinate x here? So we know the acceleration, we know the time, we know the initial position. We'll just set this to 0. We start at the origin, at the start line, and the initial velocity is 0. So how do we get to x? Which of the formulas here would we want to use for this? So think about that for a second. What's the formula that will give us x in terms of x0, which is 0, v0, which is 0, and the time and the acceleration, which are given? Well, in this case, it is indeed just simple plug and chug. It is this formula here, position from velocity and acceleration. So let's look at that here for the dragster. So we have v0 is 0 since we're starting from rest. Typically, the keyword here, if something says we're starting from rest, then the initial velocity will typically be 0. x0 is 0. We're starting at the origin of our coordinate system. In many cases, we'll actually be able to set the origin of our coordinate system, and it will be useful to pick the origin at a point that is useful to calculating the answer to the question. And in this case, setting the origin at the start of the race for this dragster is going to make sense, because it makes this x0 equal to 0, and that makes it simpler to do the math. And then we know that the acceleration is what was it, 26.0 meters per second squared. So to get x, we'll use x is x0 plus v0t plus 1/2 a t squared. So that is 0 meters plus 0 meters per second times the time plus 1/2 26.0 meters per second squared times 5.56 seconds squared. And the answer we get for that is, if you do this multiplication, you'll find 402 meters. So let's do a double check on this answer. Does this make sense units wise? Yes, both of the dimensions of x and the answer that we found are correct. We get an answer in meters. We have our square of the time that cancels with this per second squared in the acceleration. So that leaves us with just the dimension of meters. Excellent. The next question, what is the velocity at that time? So after accelerating from rest for 5.56 seconds at an acceleration of 26.0 meters per second square, what is the final velocity? So again, what's the formula that we would want to use here? We are given the initial velocity, we're given the acceleration, we're given the time, and we're asked to calculate the velocity, the final velocity. So what we're going to use now is this velocity from acceleration. We are given v0, we're given a, we're given t, so it's just plugging in and we get v, right? So v is, so this is the second part, v is v0 plus a times t. So that's going to be 0 because we're starting from rest, plus 26.0 meters per second squared times 5.56 seconds, and that is, let's see, 144.56 meters per second is the answer you should get for this. So now let's say in this problem we first calculated the velocity. Could we calculate the coordinate x from that as well? So let's look at if we wanted to calculate x from the velocity that we obtained first. So we would be using a different formula. We could be using v squared is v0 squared plus 2a x minus x0. So we can use this to calculate the velocity. v0 squared is 0 plus 2 times 26.0 meters per second squared. And let's say we calculated 402 meters first. So if we multiply these two together, we'd find something that is also 144.56 meters per second squared. So that is again another way that we would find that. We would take this product here, take the square root of it, and we would find 144.56 meters per second. So that's another approach in which we'll be able to use, which we could have used to calculate that velocity. Okay. So any questions about this problem? I see some of you are putting questions in the chat. Let me see if there's any in particular that I can quickly pick up. So I see some of you are answering each other, so that's excellent. So that that's exactly what you what I hope you can continue doing. Okay, let's look at the next problem. So after this dragster, we've determined x and v after a certain fixed time. So let's look now at a different problem where we're not actually interested about any time. So we have a car moving at 30 meters per second. The initial velocity is 30 meters per second. The car can accelerate, a negative acceleration, in other words known as deceleration in our daily life. The car can undergo an acceleration that is larger when the roads are dry than when the roads are wet. Let's say that when the roads are dry, we have an acceleration of minus 7 meters per second squared. So the question is, what is the stopping distance that this car will experience? What's the distance before the car comes to a complete stop at this stoplight, hopefully in front of the stoplight, when it starts off at 30 meters per second? So what's the formula we would want to use for this? Which one of these formulas would we want to use? We're not interested in the time. We're not going to need to calculate the time. So is there a formula that allows us to avoid calculating the time? So indeed, some of you are pointing already to this formula here. It's the last one. So that doesn't involve the time at all. It only involves the acceleration. The stopping distance, x minus x0, is the stopping distance. And then we are given the final velocity and the initial velocity. What's the final velocity here? So the final velocity here is 0, right? Ideally, you want to be stopped at the final velocity right at the traffic light, so the final velocity will be 0. So let's look at calculating the solution here. So for stopping distance, we have that v squared is v0 v0 squared plus 2a x minus x0, and I'm going to call this delta x. That is the stopping distance, right? So we're going to calculate now what delta x is in terms of v and v0. V is equal to 0. That's what it means to be stopped, right? V0 is 30.0 meters per second. And so if we want to calculate delta x, that will be minus v0 squared over 2a, or minus 30 meters per second squared over 2 times minus 7.0 meters per second squared on, this was our A dry conditions. Okay. So we can plug in the numbers here. 30 squared over 2 times 7, that will give you 64.3 meters. And you'll see that this negative sign that came from our formula cancels with the negative sign in the acceleration, so or the deceleration. So this is for dry conditions. If we now go to wet conditions, delta x, so this is part 1, part 2 is under wet conditions. Now we have minus 30.0 meters per second squared over 2 times minus 5.00 meters per second squared. And if you plug in these numbers, which are a little bit easier to do because you can do them in your head, 30 squared is 900 over 2 times 10, so over 10, so that's going to be 90 meters, not meters per second, just 90 meters. So that's under wet conditions, which of course makes sense. The acceleration that the road can provide when you're braking under wet conditions is smaller, which will give us a longer stopping distance than in the case of dry conditions. Okay. Now, let's, so these were all problems where we're plugging in the numerical values and calculating a numerical answer. Another thing that we will commonly do in physics, well, let me first point out one thing we commonly do, which is calculating a formula answer first, and then plugging in different values for one of the parameters. So here we've reused our solution for delta x in symbolic terms by plugging in first one acceleration and then a second acceleration. The other thing that we'll do often is figuring out how something depends on something else. So I'll go back here. How does the distance depend on the initial velocity? If my initial velocity is 2 times larger, what will happen to delta x? Will it be 2 times larger, which would be a linear dependence? Oops. Will it be 4 times larger, which would be a quadratic dependence? If my initial velocity is twice as large, will delta x be half as large, which would be inverse linear? So those are relationships that are important to know. And this one in particular, how does the stopping distance depend on the initial velocity? This might be one that you actually know from your driver's ed classes, because this typically gets thrown in there, that the stopping distance actually goes up by a factor 4 when your initial velocity goes up by a factor 2. So if we look at our formula here, or delta x is proportional to the initial velocity squared. So if we go to the dependence here, the dependence of delta x, which is minus v0 squared over 2a on v0, is quadratic. Or also delta x is proportional to v0 squared. So if v0 squared doubles, if not v0 squared doubles, if v0 doubles, delta x becomes 4 times larger. Okay. Something else we learned from this problem. So thinking about how something scales with something else in physics problems. Okay, so that was our constant acceleration for an accelerating car, or decelerating car, if you wish. Another example, which I'll leave for you to think about on your own, is a one car accelerating and trying to overtake another car. So this is this car in pursuit problem. We have one car that starts behind a second car. The first car is accelerating, so v1 is not constant. The second car is traveling at a constant velocity, so the acceleration is going to be 0 for this car. The first car will have a positive acceleration, and at some time this first car will overtake the second car, or will be at the same position as the second car. So this will give us two equations we have to write for x for the first car and x for the second car, and at some point those two values, x1 and x2, will have to be equal, and that will allow us to solve an equation for the time it takes car 1 to catch car 2. So that's another type of problem that you will see in this context. Okay, so much for horizontal constant acceleration. Now let's talk about vertical constant acceleration, or in other words, free fall. Again, I'm going to leave this the video that I have here on YouTube for you to watch on your own, because this is probably not going to propagate very well through the live stream. So you'll see that in the slides. But just to show you that this actually happened, in one of the Apollo missions, an astronaut took a hammer and a feather and dropped them both at the same time on the moon. So on the moon there's no atmosphere, so any kind of air resistance does not play a role. And of course, as this is visible in the video, actually, the hammer and the feather both dropped to the ground and reached the ground at exactly the same time. So why do we talk about that here in a chapter on constant acceleration? Well, because the hammer and the feather, when they're falling in vacuum and air resistance can be ignored, they actually fall with constant acceleration. This is at this point, let's consider it a curious coincidence that the acceleration for things that are falling on the moon or on Earth, that acceleration, that vertical acceleration, is constant. And it actually has a specific value, that acceleration. So if we're gonna call this free fall. Think about this as free from any kind of air resistance, free from drag, or free from, of course, any other kind of free from, I don't want to use the word force, but I'm going to use it anyway, free from forces that might interfere with the fall, So that's free fall. So in the case of free fall, now we're going to put our axis vertical, and instead of calling it x, we're probably going to call it y, because we think of y as a vertical position. The acceleration for anything that is in free fall is going to be in the negative direction. We're going to give this the symbol g, and this acceleration is minus g, now as a number, as minus 9.80 meters per second squared. minus 9.8 meters per second squared. So that is the acceleration that any free falling object will experience, and so it will accelerate downwards when it is falling. So the same formula is of course applied, so we can write now that y is y0 plus v0 times the time minus 1/2 gt squared. That's because the acceleration is minus g. The velocity will be v0 minus g times t, and v squared will be v0 squared minus 2 times gx, I almost wrote x, y minus y0. So those are the exact same formulas that we've talked about for the horizontal problem, but now they're applied to the vertical problem of free fall with a equals minus g, and a equals minus g, or minus 9.8 meters per second squared. So keep in mind, g as a symbol is a positive quantity, so this minus sign already includes the minus sign there. G is 9.80 meters per second squared. The acceleration is minus 9.80 meters per second squared. So let's do some problems with this. And of course, these are nearly exactly the same problems as for horizontal acceleration. There's only so many things you can write a problem, with 3 equations. There's only so many problems you can come up with. So in some sense, you can think of a very similar set of problems that are horizontal to the ones that we're going to do in the vertical context here now. So let's go to the first problem. Okay. Let's go to a first problem, which is this baseball problem. So a baseball hitter hits a baseball, and the baseball goes straight up. And we still want to keep this one-dimensional motion, so that's why we're going straight up, not at an angle. That will be something we talk about on Friday. So we're going straight up. We're starting at y equals 0. The ball goes straight up, and the ball comes down 5 seconds later, and the hitter catches it. So exactly 5 seconds later, the hitter catches the ball that went vertically up in the air. So the question is, what is the initial vertical velocity? And another question is, how high did the baseball go in that time? So let's think about that. And actually, let's think about what initial conditions we actually know. Do we know the initial position? Yes, we know the initial position, y0 is equal to 0. We know the final position. The final position, y, is also equal to 0. That's the position when the hitter catches the ball again. Do we know the initial velocity? No, we don't know the initial velocity. Do we know, we're actually asked for the initial velocity, right? Do we know the acceleration? Yes, we do know the acceleration. That's 9.80 meters per second squared with a negative sign to go into the negative y direction. And we know the time of 5 seconds. So if we look at this now for the baseball hitter, so we're asked for v0, but we know y, we know y0, we know the time, and we know the acceleration minus g is minus 9.80 meters per second squared. So the equation that we'll be able to use is y equals y0 plus v0t minus 1/2 gt squared, right? We know this, we know this, we know the time, we know the time here as well, we know g. The only thing we don't know is v0. So if we plug in the values here, y is equal to 0. That's when when the hitter catches the baseball again. It started at 0 plus v0 times 5.0 seconds minus 1/2 times 9.80 meters per second squared times 5.0 seconds squared. So we can solve this for V0. We can actually write V0 is 1/2 9.80 meters per second squared times 5.0 seconds squared, and this all divided by 5.0 seconds, right? So, and if we fill out the numbers here, if we calculate what V0 is, we'll find that V0 is 24.5 meters per second. Again, this of course cancels with one of the powers here, and then one of the seconds here cancels with one of the seconds in the denominator, and so that gives us the units of meters per second. So I know that at least dimensionally this formula makes sense before I even plug in any of the numbers in my calculator. So that gives us the velocity, the initial velocity with which the ball was hit up. So let's look at the next question here. How high did the baseball go? Well, now we can start thinking about this in two ways, right? What happens at the highest point in the trajectory of the baseball? What are two approaches we could use to determine how high the baseball went? So indeed, I see some of you posting in the chat that at the highest point, the velocity will be 0. Instantaneous velocity will be 0. It actually changes sign. The velocity goes from pointing in the positive direction to pointing in the negative direction. So at that point, the velocity is equal to 0. What else might be a way to determine this? Oh, I see Samuel is pointing out that at the highest point, the time will be half that of the 5 seconds. So the time will be 2.5 seconds. So indeed, if we want to calculate the highest point, we can use either that the time is at 2.5 seconds, and then we can use y is y0 plus v0t, and we now know what v0 is, minus 1/2 gt squared, with t is 2.5 seconds. Or we can calculate this using our velocity from acceleration and distance. So we can use v0 squared is v squared is v0 squared minus 2g y minus y0. So in this case, the velocity is 0 at the highest point. That's instantaneous velocity is 0. We still know v0 here, and we know g, and so we can just calculate y from this. In both cases, we should of course find exactly the same answer, right? And in both cases, we will indeed find the same answer, and that answer will be, let's use for example the first approach there. So if y is y0, which is 0 plus v0, so v0 times 2.5 seconds minus 1/2 9.80 meters per second squared times 2.5 seconds squared. If we plug in those numbers, we'll find 30.6 meters. In the second approach, we're going to calculate y is now, so this is 0, so that will be v0 squared divided by 2g. So that will be our 24.5 meters per second squared divided by 2 times 9.80 meters per second squared. And if we plug in the numbers here, we'll find out that this is exactly, of course, 30.6 meters as well. So of course, in a surprise to no one, we find that if we calculate the same thing using two different approaches, we find, of course, the same value for those two solutions, or for that one solution, right? Okay. So let's close out with that. One other type of problem is giving is allowing a vertical rocket to release a booster. So the booster starts off with an initial velocity that is still in the positive direction before it then, of course, also changes direction and falls down. I will say one more thing, which is about integrals and calculus. For those of you who have gotten some course in calculus already, you'll recognize that we're talking here about derivatives. The velocity is the derivative of position, the acceleration is the derivative of velocity, and of course, if you've seen integrals, then the other way around is true as well. The velocity will be the integral of the acceleration over time with some arbitrary constant, and the position will be the integral of the velocity over time with some arbitrary constant. And those arbitrary constants will be determined by the initial conditions, and that's exactly what the x0 and v0 are going to be. So all of that will look familiar. Essentially, if you know calculus, there's only one formula, and it's this one here. If you don't know calculus, there's a couple of other formulas that that essentially are coming from the same math behind it. And that's it for today. So we'll talk again in 2 days, and I'll be hanging out here in front of the auditorium in case there are any questions.